Okay. Okay, so now let us move to the next big achievement. Actually, this achievement is called something called the fractions. Again, this idea was there, but you need to write down how to properly write down fractions. This idea actually came from something called this Middle East. So this modern day it is called the Iran, you know. So Baghdad was the capital of Iraq, and there was a famous mathematician, Persian mathematician lives. His name is okay. Before that, let me tell about that how it's invented, what this idea discovered. The idea of these fractions actually influenced by something called the Quran. You know the name Quran-e-Sharif. So Quran-e-Sharif has influenced us to get the idea of fractions. How? So, for example, see so far, have you seen the measurement system in USA? They don't do in the metric system 10. They do always subdivision of twice, right? This is called dyadic subdivision. You take a big thing, you divide into two portions. Then the small portion you divide into two portions. So by that they make something called pounds. Then 1/16 of that is ounce, right? Because it is easy to divide it. So you have something. You don't know how much this is that, but you can also say that okay, this much is half, this much is another half. Then this half you take half. So this process is called the process of division, something in the two-adic. So in number theory we call it two-adic subdivision. Okay. So this method has a major drawback, because if you allow this two-adic subdivision, your problem of multiplication, division, addition will be more difficult compared to the metric system which Aryabhatta introduced. Okay, so Quran-e-Sharif, so before Quran-e-Sharif in Bible they used to do always subdivision. What does that mean? So I have hundreds of animals and I have two sons, so I will divide half. Okay, they have another two sons, they will divide half. You understood the subdivision. So whenever you divide this two-adic biadic subdivision, you will never get the fractions in that sense. You will get kind of equality, always equality. Equal, first person is equal, second person equal, like that. But Quran-e-Sharif says no, not everything is equal. You can give someone to extra, someone to less. Okay, you can give, you love your say elder son or younger son, you can give a bigger proportion to him, right? And someone you can give less proportion. Now you cannot do half process. So the process of Bible is not going to work here. You understood? Then you need a different systems which can measure this idea of fractions. So this idea of fractions came from this book called Quran-e-Sharif, or Quran, and it was first. So obviously people also knew this thing, but the first person who wrote it down, his name is Muhammad ibn Musa al-Khwarizmi. Have you heard the name? He was a Persian mathematician around 700 and 760 CE. Okay, he was from Baghdad. Baghdad is now modern day Iraq, the capital of Iraq. Okay, now which is full of lots of ISI, some lots of things, but it was those times it was a hub of science and technology. Okay, and this person is not only inventor of this idea, he is also inventor of the name called algebra. Have you heard the name algebra? You learn, right? Algebra. The algebra name came from the Persian word al-Jabr. Al-Jabr means you unite the broken parts of the things. Okay, and he wrote, along with another mathematician, he wrote something called calculation of Hindu numerals, because after Aryabhatta Hindu numerals were very famous, and these two persons they started promoting this Hindu numeral all over the world. Okay, and he wrote a book name is Al-Kitab al-Mukhtar fi Hisab al-Jabr wala Mukawwala. Mukawwala means some kind of not fight, yeah, some kind of competition, exactly. So he used to pose some problems, and then he asked that people come and do the competition, and whoever win will get the prize. And those problems he wrote down in these books called Al-Kitab al-Mukhtar fi Hisab al-Jabr. Al-Jabr is the term which actually derived the modern days called algebra. Okay, algebra came from these terms. Okay, so he was a very famous mathematician. So done. Okay, so now, so how much we have learned so far? We learned that we have characterized the numbers, how they invented. So let me just give you a pictorial view so that you can understand. For example, we have this, I will write down, I will tell you what are those things modern day. So we learn the real number, complex numbers, then we have this natural number numbers, which is of these forms. 1, 2, 3 of these forms. Then we have the integers, which are not only the whole numbers, you also add in that set the negative of those numbers. Then we have rational numbers. So rational numbers are nothing but integer along with the fractions. The fraction idea you already learned how it is invented. And then you can obviously you can have many representation of this thing. We generally use something called the irreducible representation. For example, so this number 6 by 10, we will say this is actually 3 by 5. Okay, so 3 by 5 means that your numerator and denominator has no common prime divisors other than 1. So the GCD has to be 1. So this kind of representation is called the irreducible representation of rational numbers. Okay, yeah, so I wrote it also, irreducible representations. And then you have such number which you cannot write down of these forms, and those numbers are called irrational numbers. Okay, you cannot write down of this form. For example, you have root 2, root 3, root 5. These are all irrational number. You cannot write down of this form, the fractional form a by b. Okay, and there are many proofs available. Maybe I will give you a geometric proof to understand what happening here. Root 2 minus, exactly, because this is 1, 1. So this number is, original number was 1 plus root 2, and then you take minus 2, so it is nothing but root 2 minus 1, right? So length of this smaller side is root 2 minus 1, length of bigger side is 1, right? Is that clear to everyone? Now we see that the originally, what was the ratio of the length? The larger side was 1 plus root 2 and the smaller side was 1. So ratio was exactly 1 plus root 2, right? Now let us try to ask what happened. Huh? Now let us try to see what is the ratio of the length of these two sides. What is the larger side here? 1, and the smaller side is root 2 minus 1, right? Now you see that this number is exactly 1 plus root 2. Can you see this? No? You multiply both sides, okay. Okay, so process of cutting 2 square is also 1 plus root 2. Again, you can again cut 2 square. That's why I wrote here. Okay, so before that, let me discuss about root 2 also little bit. So this number actually appear in the work of Bodhayana. Bodhayana was an Indian ancient mathematician, and he wrote many books. One of the books is called Vedic Shulba Sutras, around 800 BC. BC means before, BC means before Common Era. Okay, so Bodhayana actually calculated these 5 decimal places. He had the idea of those things, and then his student from that same group of mathematicians, his name was Manaba. ठीक है सर. Sir, oh, हाँ, it's not working. It's working now? No. Okay. Oh my God. Huh? Okay. Done? Now? Okay. So the Manaba actually find out that these numbers is not, it has not, whatever the number they know. So the high concept of irrationality was not there, but he knew that this is not the natural kind of number, it has something unnaturality. The first person who actually give a proof of irrationality, his name is Hippasus of Metaphontum. Metaphontum is a part of modern day Italy. Okay, he gave the idea of proof of. So plug, you need to plug, you don't give only the wire, no, without plug. Fine? Okay. And later theorists actually compute the irrationality of the other number, root 3, root 5. And this you can find out the dialogues of Plato. Plato wrote lots of dialogues. Inside that you can find out these ideas, okay, that these numbers are not rational numbers. Okay, so now what I was talking about, the geometric proof, that you start with a rectangle of sides 1 and 1 plus. What is the time? 12:10. Okay. So do you have converter? Then we can put it into USB? No. So converter is there. This is HDMI, right?
Yes, sir.
So you put a HDMI to USB converter. No, it will be easier. So you take this a converter, HDMI to USB. USB, you have USB and HDMI converter. Adapter. Huh? One. No, you need one side is HDMI, another side is USB port.
HDMI adapter.
Adapter. Play the game again. You can again cut two smaller rectangles, a smaller square, and you have come out with a smaller rectangle, even a smaller one, right? Now you do this small calculation saying that the new smaller rectangle also have the same ratio. So what does that mean? That means you can continue this game again, right? You understood? So this process must not stop, right? You understood? But problem is that if root 2 is a rational number, then what happens? Then this process will stop. Why this process will stop? Because when you take the ratio, see, after final step it will stop, because the denominator of the side length. So if you take this denominator, so what does the denominator do? This is not increasing, right? This is either decreasing or same. But numerator is actually, you see, numerator always decrease. So originally it was 1 plus root 2, then become 1, reduce, again become reduced, right? So after finalizing this step, if it is a rational number, it will stop somewhere. And hence you can show that this 1 plus root 2 cannot be a rational number, which gives you the proof that root 2 cannot be a rational number. This is one geometric way to prove. You must have learned many other proofs that you take square in between 2 and 3, right? There are so many proofs are there in between 1 and 2 and so on. Okay, so this is geometric way to understand root 2, and which is the number of this form 1 plus 1.4142 dot dot dot, these numbers. So the method I discussed, it has a name actually. Can anyone tell me what is the name of this method? This is called continued fractions. Okay, this method is called the method of continued fractions. So what I did, I wrote root 2 is of these forms, 1 plus 1 by 1 by root 2, and then again I did the same process. The root 2 is here also root 2 is there, so I will replace the same idea here also, then I will have this and so on. So this is called the continued fraction method, and by this thing you can clear that this will never stop. You understood? So and this expression is called the continued fraction expression of the root 2. Okay, so now coming to the just let me give you some basic idea. A real number is rational if and only if. So in the binary or decimal, any expression, if it is actually periodic, then only it can be rational. You can say, for example, this is a rational number. So or you can write down 499999999. So this is a periodic number, right? After 4 the 9 repeats, right? And you see that these numbers are same actually. This is also rational number. So in binary or decimal representations, in the same real number you can have more than one representation, right? But this is not the case for continued fraction representations. In the continued fraction representations, this is rational if and only if this must be finite. This is so nice. So whenever you have a numbers and if you know the control fraction representations, you check whether it is finite or not. If it is finite, then must be the rational number. If it is not finite, it cannot be rational number. For example, in this case, it can be finite or infinite, but both are rational numbers and both are same actually. Okay. On the other hand, if you take the control fraction representation, it is not possible. So what does that mean? That means control fraction representation are more natural compared to the decimal representation of binary or hexadecimal, whatever you want. In comparison, you also learn hexadecimal, right? But these are not so natural as control fractions. Okay. In fact, the real number whose control fraction is periodic, they are actually coming from degree 2 irrational number. I will discuss what is that. So let us call quadratic irrationals like this: root 2, root 5, root 2, root 3. They are called quadratic irrationals or degree 2 irrational. What does that mean? That means these numbers satisfy a polynomial of degree 2. What does that mean? So if we take a polynomial fx equal to x square minus 2, you see that this number actually satisfies this polynomial, or this is the root of this polynomial, right? These are called degree 2 irrational numbers. And only for this case the control fraction will be periodic. These are theorems, probably you may learn later. Fractions of these forms, some 3, 5, 7, 9, and you stop here, then you say this must be rational number. It cannot be rational number. Okay, you can easily construct. But if I give a number, finding out control fraction also not so easy, not always so easy. Okay. Now let me give you another very interesting idea. So this is called algebraic numbers. What does that mean? So you see that there are numbers which satisfy the polynomial equation. For example, root 2. Root 2 satisfy this equation fx equal to x square minus 2, right? There is some number Sarah was teaching about complex number, the iota. Remember iota? Now you see that iota satisfy this polynomial x square plus 1. Okay, isn't it? Similarly, all the rational numbers satisfy some polynomial equation. For example, 2 is satisfied by this equation fx equal to x minus 2, right? So there are numbers which actually roots of some polynomials. Okay, so those numbers are called algebraic numbers. Is that okay? You understood? Root 2, root 5, iota, 2 iota, 3 by 5. 3 by 5 is algebraic. What do you think? If you take a fraction 3 by 5, is it an algebraic number? Is it satisfy some polynomial? What is the polynomial? For example, if you choose, there are many polynomials, so you can choose this, right? 5x minus 3, this is polynomial over integer I am taking, right? You see that 3 by 5 satisfy, right? So what does that mean? That all the rational numbers are algebraic numbers. Other than rationals, you also have some numbers like root 2, root 5, even some complex number, they are also algebraic numbers. They satisfy some kind of polynomial equation, right? But then you can ask whether all the numbers are of these forms or you have numbers outside this world or not. What do you think? Any number you can write down as a root of some polynomial? What do you think? Yes? No, unfortunately the answer is no. In fact, these numbers are very small. In terms of analysis, we call these numbers are having something called the measure 0. I mean, no, even rational coefficients also. Even rational coefficient you cannot find out everyone. Even with algebraic coefficients also you cannot find everyone. If you take algebraic numbers as a coefficients, then also you cannot find everyone. In fact, whatever you can find out, they are only something called countables. Countables means they have something called the Lebesgue measure 0. Okay, so let us not go into that. Okay, so for example, like rationals are all algebraic numbers, and then root 5 algebraic number. It satisfies the polynomial x square minus 5, I square root of minus 1 is also algebraic numbers. It satisfies the polynomial x square plus 1. Okay, in fact, if you collect all such numbers which coming out of some polynomial, roots of some polynomial, this set is called the something called the algebraic numbers. Okay, and this set we denote by q bar. So q bar is what? Q bar is you collect all the numbers, say a, such that f of a equal to 0, where f x is a polynomial inside qx. What does that mean? That means it's a polynomial whose coefficients are from rational numbers. Okay, and you collect all such roots, and this set we call it q bar, algebraic numbers. Okay, and it is easy to show that. Okay, you need some more mathematics, but it is not difficult to show that these numbers are actually forms a nice structure that is called the structure of a field. Probably you have learned field yesterday's talk, right? Yesterday Prem was speaking about finite field, other thing, right? Field has two operations, addition and multiplication, and they satisfy few relations among addition and multiplication, right? Algebraic numbers are same. If you add two algebraic number, it will be again an algebraic number. If you multiply two algebraic number, it will be again an algebraic number. Okay, so they forms this structure of field. Okay, and then the number which does not have any kind of, they are not coming from any kind of polynomial, these numbers are called the transcendental number, which are not inside q bar. Okay, so inside the complex plane, suppose this is my complex plane, and I just write down all the numbers which I can write down in terms of roots of sub polynomial. So there will be some rational integers, some complex number. And if you collect all such numbers, that will be my q bar. But this collection is very small. Even on R also, real line, if you take all the rationals, all the integers, okay, all the stars, you know stars, right? Root 2, root 5, root 7, root 13, 1 plus root 2. If you collect all such things, still this is very small compared to the real numbers. Okay, you have more numbers out of this set. Clear? And this collection of numbers, they are called countable. Countable means you have, okay, so you can have a bijective relations from a countable, say natural number or something. It's called the countable sets. Okay. But the numbers which are not coming from the roots, they are more actually, they are something called uncountable. Okay, so they are more, though it look like that all the numbers are of the form root 2, root 5, but they are actually very small compared to the other numbers. Those other numbers we call transcendental numbers. I wrote here transcendental number, which is not an algebraic numbers. Is that clear? You understood? Algebraic, transcendental. So far you learn rational. Now you learn algebraic, transcendental. There are more division in transcendental number, but I don't want to go there. You can further divide transcendental into U number, S number, T numbers, more division, but let us not go into more details. Okay. So let us learn algebraic and transcendental. Now the question is that how do you know? What is the point you understood that there are more numbers which are not of the form that coming from a roots of some polynomials. Okay, so this is a famous story due to the French mathematician Liouville. This person Liouville, and he is the first person who defined this kind of numbers, which nowadays called Liouville numbers. The first number what he proved, this is the number first, 1 upon so 10 factorial or n factorial or 10 to the power n factorial, whatever. It doesn't matter, you choose whatever. These numbers has very peculiar properties. These numbers actually you cannot write down as a root of any polynomial. Whatever polynomial you choose, you cannot write down. Obviously here you can write down any rational, irrational number, doesn't matter. All have the same property. These numbers are called Liouville numbers. Okay. Now what was the advantage of why this number originated? So this is a famous story of Dirichlet. So let me share 2 minutes, give me 2 minutes. So how much time I have? 12:30, okay, so I have some more time. So there was another French mathematician Dirichlet who proved that the rational numbers are very nice actually. What does the meaning of nice? Nice means that they are some kind of dense inside all the real numbers. What does that mean? You choose a rational number, whatever neighborhood you choose, whatever small neighborhood, there will be another rational number sitting there. And same thing is true for irrational number also. Irrational number also forms a dense subset of real numbers. Okay, so both rational and irrational, they are dense. So given any real number or in any real rational number, if you find out any small neighborhood, for example, you give me a real number. For example, say 3 by 5, okay, and give me a neighborhood. So neighborhood is say probably 0.0001, okay, 0.0001. So there, so somewhere 3 by 5 is here, and then you have small neighborhood. Whatever small neighborhood you choose, you will have another rational number here sitting there. Why? Because you just average it, or you take so what you can do, you can take 2 times this, 3 times this, and then divide by 5 also. That also again a rational number. Okay. Any combination of these numbers will be again a rational number, and they will be sitting inside this. Okay. So you can always find out rational numbers in between any small neighborhood. Okay. So this property is called the dense property of rational numbers. Okay. But there is a catch. So this is true for not only rational number, this is true for irrational number also, true for any algebraic number also, right? But Liouville is the first person who showed that algebraic number, though they are dense, but they always keep some distances with rationals. What does that mean? They are class friend, but they are not the best friends. You know the best friends and class friends? Okay. So algebraic numbers are those numbers, though it satisfy the property of Dirichlet, but still the moment you have a rational number, it always keep a distance to the rational number. It cannot go very close. Okay. So this is the property which Liouville understood, and he realized that there are numbers which can go very close to you, as close as possible. It will not create any distances, and those numbers cannot be algebraic numbers, because algebraic numbers always keep a distance with the other rational numbers. You understood? So algebraic numbers are classmates, they are not best friend. But the numbers which are best friend, which are transcendental number, it will reach very close to you, like Chaddi Buddy, you know, the very good friend. You wear his t-shirt, he wear your t-shirt, happen, right? It happened, right? Like when we are college students, somebody comes and give me your t-shirt, take it. This kind of friend. Okay, so that's why Liouville understood that there are numbers which can go as close as possible. Those numbers cannot be algebraic numbers, and this is a famous theory of Liouville's. From that we got the idea of transcendental number. Okay, now obviously Liouville proved that all numbers are transcendental numbers which are of these forms. Okay, and then later many people came and developed the theory. One of the person named Hermite, and he proved that this number E, have you seen this number E? 1 plus so on, and he proved that this number is also transcendental number. It cannot be. So this number, have you seen this number E? So this value is what? So some 2.71, 8281, 8284, 59045, something like that. So this number also is not algebraic numbers. Okay. Do you know how this number, why this number invented or they discovered here? The story, you know that? Anyone? So this number has a very nice story. It's called Euler number, but Euler did not invent it. Euler is not the person who invented these numbers. This number invented from a social problems. Okay. So let me tell you that before Hermite proved is transcendental, this problem was there from long time. What was the problem? Suppose you have 1 rupees and you are keeping in a bank, and at the end of the year they are giving you 100% return, then how much you will get after 1 year? Anyone? 2 rupees, right? 1 rupees, 100% return, 2 rupees you will get. Is that clear? But instead of getting your return after end of 1 year, if you take the 50% return on after 6 months and rest of the 50% after 6 months on the compounding of the first amount, okay, then is it more or less? What do you think? Do you understand what I am saying? So you have 1 rupees and you want to take 100% return after 1 year, you will have 2 rupees, right? But you say that no, give me the interest 50%, not the full, half, make it half. But give me the half of the month, half of the year. And then rest half on the total amount. So after 1 year, kya hoga then? After 6 months, you will get 50% of 1, means it will becomes 1.5. This is 6 months, remember. Okay. Now after 6 months again, you will have 50% of this amount. So what is the amount? 2.25, something like that. Because 50% of this is nothing but 0.75. You add it, so it will become 2.25. So the same 100% interest you are taking, but you are not taking together. You are taking kind of something called compounding. Now once you compound those things, your sum become more, right? Now can you do this process for quarters? You know quarters? Quarter means 1/4, or maybe you can do it process 1/3, 1/3, 1/3. Do you have a better number, bigger number? What do you think? If you instead of compounding 2 times, if you compound 3 times, are you getting a bigger number, bigger sums? Yes, obviously. 4 times bigger one, 5th time bigger one. Now suppose I am telling you, you will get interest every day. 1 rupees, after 1 day you will get interest of 1 by, so total interest is divided by 365 days. And next day again you are getting interest of whatever the sum on 1 upon that, and do the process. Are you getting a bigger sums, right? Is that okay? Now this was a very big challenge, that if we continue this process, can we reach a big number as large as possible? The answer is no. Okay, so this was first proved by the mathematician named Jacob Bernoulli. Jacob Bernoulli showed that this process has a limit, and the limiting value is E. So if you continue this process, the maximum you can get it from 1 rupees is 2.7182818284599045 ... This you cannot go. You cannot make this process with the same return, 100% total return. You cannot go to 10 rupees or something from 1 rupees. Okay, so this is the history of that E. Okay, though we call Euler number, but this idea, this is first discovered by this Bernoulli, Jacob Bernoulli. Okay, is that okay? But later Hermite showed that this is not only a irrational number, this is a transcendental number, more than irrational number. Okay, and this is the work of Hermite in 1873, who proved this number is transcendental number. And then there is another famous constant, probably you know, is called pi, ratio of circumference by the diameter. Whatever circle you choose, you see the ratio is always constant. Okay, and this is also a transcendental number, and this is due to someone called Lindemann, another French mathematician. Lindemann proved that this number is also transcendental. It not follow any kind of algebraic property. You can go as close as possible to pi with rational number. Okay, this is very friendly. Okay, they are not like classmate, not best friend. They are very best friend. Okay, this kind of numbers. Okay, maybe how much time I have? Maybe I can. Okay, so quickly just finish this thing. So I can just pose some questions to you, and then I will leave. For example, what about if you add 2 numbers? Suppose you have E and pi. If we add, it will be of this form, right? 5.859 something like. So I can ask you the same question: is the rational number, irrational number? What do you think? Rational number? Okay, whoever proved this thing will get a Fields medal, because this is an unsolved problem. Anyone who proves that E plus pi is transcendental will get a Fields medal. Obviously, you have to be under 40 years old. After 40 you will get Abel price. No problem. Abel price is also very important price. So you said transcendental, but this is not known. See, question is so easy, right? What about these numbers? If you multiply these two numbers, pi and e. Transcendental, algebraic, rational, irrational. Now say. Unfortunately, we don't know. We don't know whether the product is again transcendental or rational or not. Because transcendental number does not form the structure of a field. So you cannot say that if you multiply two transcendental number, again it will be transcendental. Or if we add two transcendental number again. Okay. So what is the advantage of algebraic number? Algebraic number has a field structure. So you can do multiplication, division, addition, everything on there. You cannot do same thing for transcendental numbers. Okay. So anyone who wants to prove this thing will get a Fields medal. Again. You know Fields medal, I hope you know Fields medal probably. It is the highest award in mathematics given, because in mathematics we don't have Nobel Prize. We have something called Fields medal if you are under 40 years age, and for your lifetime achievement they give you something called the Abel prize. Okay, we don't have Nobel Prize. So Fields medal is equivalent to the Nobel Prize of mathematics. Okay, then what about this number, logarithm of pi? So you know pi, you take natural logarithms. What about these numbers? Rational, irrational, transcendental. Any of the question, if you have solution, you will get a Fields prize, Fields medal. So you understood? These problems are so easy to pose, but the answer is so difficult to find out the answers of this problem. There are many such problems. You can work on these areas of transcendent fields. These are all unsolved problems. Okay. With that, let me thank all of you. Thank you for such a lovely audience listening to me. Okay. I will be happy to answer your questions. Whatever question you can ask me. I will be happy to answer. This is my picture at my office, old office. One of my students took with a very bad camera, so the resolution is not so good. Okay. Okay, anyway, thank you. Please feel free to ask questions, whatever question you feel. Huh? Real number example I gave you that 1 by 10 to the factorial n. You can choose any number. So you just randomly picked here, or you randomly picked here. For example, here you write down, so all real numbers, or n factorial plus some function. So it should not be, it should be something which has more zeros in between. Then they have to be real numbers. Okay, you write down 2 over n square whole square, whatever you choose. These all are real numbers, and they all are transcendental numbers actually. In fact, they are something called U1 numbers. Okay, so transcendental number also you have subdivisions. You can divide transcendental into 3 categories. It's called U number, T number, S numbers, and they are all something called, even inside U number there are subdivision. U1, U2, U3, U4, U5, U infinity, all are going. So the real numbers are actually comes under U1 numbers. Okay. Similarly, if you take the square root of real number, they will be inside something called the U2 numbers, and so on. Okay, so this is a big category. I mean, you can categorize all the numbers in terms of these numbers. Any other questions? Oh, we don't know. We don't know. But we know at least one thing. For example, I can tell you something interesting. So if you give me e plus pi and e minus pi, the both cannot be algebraic. At least one has to be transcendental. That I can tell you. Both cannot be algebraic. Why? Because if both the numbers are algebraic number, you can add those numbers and it becomes algebraic. But neither e nor pi is algebraic numbers. So if you give me e plus pi and e minus pi, at least one has to be transcendental number. They both can be transcendental obviously, but they both cannot be algebraic. You understood? Same thing for E into pi, E divided by pi also, same thing happened. They both cannot be algebraic. Clear? So you know at least one has to be transcendental number out of that. And there are many, so the transcendence theory is begin from here, well the work of Liouville's, and then it goes on and on and on. Those are interested, they can learn more actually. Any other questions? Please. Okay, so we learned that how the number system developed from the ancient Babylonian civilization, then Egyptian, Sumerian, then Greek mathematician came, then Indian mathematician, Persian mathematician, right? And slowly developed all the theory. And now we came to the modern day number systems where we know many things about the number and we don't know many more things about the numbers, which is still unsolved. Okay, one of such problems we will discuss in the afternoon is attached to something called Riemann zeta functions, and a very big problem is called Riemann hypothesis. I will discuss very basic ideas of that things, zeta functions, and the Euler proof, how Euler got the concept of those numbers. I think I remember yesterday Sarah has shown that, you remember 1 plus 1 by 2 square, 1 by 3 square, this series converges and converges to the number pi square by 6. Okay, and there are many proofs. Okay, in fact the famous proof is due to using that Fourier series, but Euler did not use Fourier series. Fourier came after Euler. Euler is much before Fourier. Okay, so Euler proof is very interesting. I can give you that proof of Euler to discuss that convergence and other things also. Okay, so afternoon talk, don't miss it. It will be more interesting. So this is just beginning. Okay, okay, bye.